Alright, welcome back to another video on my channel, math_exe, and today we're going to look at a type of exam question that we'll often see when dealing with linear inequalities. So this is like the type 1 that I will show you. So it asks you to solve a linear inequality, and then you need to find the smallest or sometimes greatest value of a variable if given these criteria. So in this case, if x is an integer or a prime or a multiple of 4. So first, of course, we're going to solve the a part first. We're going to solve this inequality real quick, and it's pretty quite simple. So we have 2x minus 3, and it's greater than 7. So we can just add 3 on both sides to get rid of the negative 3. This and this will cancel quite nicely. We're left with 2 is greater than 7 plus 3, which is just 10. Dividing 2 on both sides, you can get that x is greater than 5. So I'll just write the answer right here, right there. So for the part B, we're going to find the smallest value of x if x is an integer. Well, this is pretty simple, I guess, and all you need to do is to kind of like count from the boundaries of this equation, in this case 5, and then just go up and see what smallest value of x is an integer. So I'll just write for the BI part. So let's check at 5. However, 5 does not satisfy this inequality, because if we substitute x equals 5, 5 is greater than 5, this is a contradiction. So if we approach this case, we're going to go to the next integer, which is 6. And notice that 6 does satisfy this inequality. So if we approach a value that satisfies the original inequality, then therefore that value is the smallest or the greatest value. So in this case, our answer is 6. So for the next one, we'll do the same trick, except this time we're asked to do if x isn't prime. So like I said, we're going to do that again, but so we check that 5 does not satisfy this inequality. Let's check 6. However, 6, notice, can factor like 2 times 3, and therefore this is not a prime. So let's check the next integer. Let's try 7. And notice that 7 is a prime because it cannot be factored into like 2 times something or 3 times something. So therefore our answer for the BII part is 7. So for the next part, if x is a multiple of 4, and again we're going to do that again, except we can just try to count from the multiples of 4. Notice I'll just write the list. So we have 4, 8, 12, 16, and so on. And we can just check from the smallest if this satisfies this inequality. Notice 4 does not. 8, however, is correct, and every else after that is correct. However, we're going to take 8 because this is the smallest possible value. So our answer for this part is 8. And we're going to look at some other examples about this type of question. Alright, so this is the second example. So we're going to solve this inequality right here, and then next we're going to find the smallest value of q if q is given a rational number, an integer, or let's scroll down a bit, or a perfect square. So first we're going to solve this inequality right there. So I'm just going to scroll down the board. over 3 plus 4. And let's just double check right here. There we go. Okay, so first we can just subtract n by 8q over 3 on both sides. So the left hand side of this term will cancel. Oh, nice. So this and this will cancel. And we can just look at this 3q as 9q over 3. And then we're supposed to subtract 8q over 3 on both sides. And we can just work out this very nicely to get positive q over 3. So we're just going to plug that in. So we have q over 3 is greater than or equal to positive 4. Multiplying 3 on both sides, so the denominator will cancel. And we're left with q is greater than or equal to 4 times 3, which is positive 12, right there. Okay, so next we're going to solve the b. I'm sorry, this is supposed to be I, and I. There we go. So first we're going to solve for the rational numbers, and rational numbers mean some number that can be expressed as a fraction, or in other words a over b, something like that. And notice our bounds, we can just include 12 right here, because we have, if we substitute 12 right here, 12 is greater than or equal to 12, which just satisfies the inequality, and it's true. And notice real quick that 12 can be expressed as 12 over 1, right? So this can be also expressed as a rational number, and therefore our answer for our BI part is, I'll just write that real quick. So for our BI part, the answer is 12, like so. And we're going to look if for integers q, smallest integers value of q. So yeah, and notice that 12 is also an integer yet again. So if we plug in 12, which to satisfy this inequality, and 12 itself is an integer, then therefore our BII part is also 12. And for III part, we're going to look for perfect squares, and I'm just going to write the list of the perfect squares right here. So 1 squared, which is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. So we can just plug in these to our original result here. So notice 1 does not satisfy this, 4 does not satisfy this, 9 does not satisfy this, 16 however satisfy this, and all values above 16 satisfy this. But we're going to take 16 because we're looking for the smallest value. So our answer for our BII part is 16. And I think we're going to look at one last example and then we're done. Okay, so for the last example, we're going to solve this inequality, and then we're going to find the maximum value of x if x is an integer or a perfect cube. So let's get into solve this inequality. We're just going to rewrite this. So first we can just subtract 3 over 5x on both sides. And then we can just look at x as 5 over 5x. Now this is just the same. And we can just make things way easier to calculate this this expression subtracted by this expression. So notice that this and this will cancel, leaving us with a 4 on the left hand side. We have 5 over 5x minus 3 over 5x, which is this 2 over 5x. And then we can just multiply by 5 real quick. So we have 20 on the left hand side is greater than 2x. Dividing 2 on both sides, we can get that 10 is greater than x. And then if we can just flip this, we can just get x is less than 10. Alright, so for the b part, we're going to solve first for integers. So we're going to find the maximum value of x if x is an integer. So since we're looking for the maximum value, we're going to just look at the values from above to below. We're going to look at the decreasing values of x. So starting at positive 10, notice that positive 10 doesn't satisfy this inequality. Just by logic right here, it's just a contradiction. Let's look at the integer below 10, which is 9. And look that 9 satisfies this inequality. And therefore, we have found 9 as our answer for our BI part. Next part, we're going to look at the maximum value of x if x is a perfect cube. And what I mean by perfect cube is a number that can be expressed as like so, n to the third power or n cubed, something like that. First, I'm just going to rewrite the sequence of perfect cubes. So if 1 cube, which is just positive 1, 2 cube, which is positive 8, 3 cube is 27, 4 cube is 64, and so on. And then we can just check if these satisfy this. Notice that 1 satisfies this, 8 satisfies this, 27 does not, and every single one after that does not. However, notice we're going to find the maximum value, and therefore 8 is the answer, since we're looking for the maximum values. So yeah. And anyways, I think that's it for this video. Thank you guys for watching. Subscribe for more videos, and I'll see you in another video. Bye bye.